This is lesson 3 of chapter 8. In this lesson, we'll talk about Lewis structures. So any molecular compound or any covalently bonded compound can be represented with a Lewis structure. And these representations show the bonds and the non-bonding electrons and how they are arranged around the molecule. You should have learned how to do this in Chemistry 1, and if not, or if you forgot, we will outline it here. So the first thing we do is we total the number of electrons available for bonding. So we'll sum the number of valence electrons. Remember, valence electrons are the electrons in the S and P subshells. So for phosphorus, if you take a look, phosphorus has 2 in the S and 3 in the P for a total of 5 valence electrons. Usually you can take this down from the group number. For phosphorus, the group number is 5, and it has 5 valence electrons. Chlorine has 7. We have 3 chlorines. We must multiply that by 3. This gives us 21, plus 5 gives us a total of 26. So 26 valence electrons is how many these atoms bring to the molecule. Now, if you have an ion, say if you have yourself an anion, something like ClO2-, then you'll have to add one more electron due to the negative charge. If you have a positive ion, so like NH4+, you'll have to subtract an electron because of this positive charge. Step 2 then is we arrange the atoms by putting the least electronegative element in the middle. Now, except hydrogen. Hydrogen can never go in the middle because hydrogen can only have 2 electrons around it. And here it says the formula will give you clues as to which to put in the middle. So if the formula says PCl3, then that kind of tells you P must go in the middle. Most of the time, this will work. And then you will connect each atom by a line. Remember that each of these lines is a bond, which is equal to 2 electrons. So in this case, we have 2, 4, 6 electrons distributed already, and then we have 20 left over to distribute. The next slide will show us how to distribute the electrons. Here it says we fill the octet of outer atoms first. Octet meaning, remember we talked about how the octet rule says that every element must have 8 electrons around it. So we'll begin by putting them on the outside. So in this case, we've put 6 more on this chlorine, 6 more on this chlorine, 6 on this. And we have 2 left over. And those last 2 we will put on the phosphorus. And that is in the final slide here, or in the next slide. Notice we'll put the last 2 on the phosphorus. This ensures that every element has an octet. If you notice, this chlorine has 1, 2, 3, 4, 5, 6, and then 7, 8 electrons. The phosphorus has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Everyone is nice and happy. And notice that our final count is 0. In other words, we've distributed all the electrons. If you run out of electrons before every element has an octet, like in the case here, then we'll have to form double or triple bonds. And the way we do it is by allowing the nitrogen to share electrons with the carbon. So the element that does not have enough, in this case the carbon doesn't have enough electrons, we'll ask the nitrogen to go ahead and share these electrons as double bonds. Anytime you do this, you don't decrease the number of electrons nitrogen has, so you won't remove its octet, you won't destroy its octet, but you'll increase the number of carbon has, allowing it to have an octet. And then finally, if you have an ion, a polyatomic ion, we use brackets. So in this case, if this was a polyatomic ion, we would put brackets around the whole ion, is the idea. We'll do a few of these examples here in a minute. But before then, let's recall that if you have a single bond, that is the longest of them all. The double bond is shorter, and the triple bond is the shortest, and also the strongest. So this is actually, the weakest bond is a single bond, and the strongest bond is a triple bond. This is good information as we continue on here. So why not we try a few example problems. Here we have, draw the Lewis structure for 3 of these substances. We have CO2, we have SO4 2-, and we have HCN. Let's go ahead and do CO2 on this slide, and we'll do the next 2 on the next. So for CO2, carbon dioxide, the first rule is go ahead and total the number of valence electrons. From carbon come 4. From each oxygen comes 6. We have 2 of those. So 6 times 2, 12. We got 16 total. We'll distribute 16 electrons around the whole molecule. The next step is arranging them. So we'll put carbon in the middle. First of all, because carbon is less electronegative, and second of all, is because the formula gives us that clue. We'll put the oxygens around the outside. Connect everything with single bonds. This gives us a total of 4 bonds. Notice we have 2 here, 1, 2, 3, 4. 4 electrons. 2 bonds, 4 electrons. Let's keep going until we reach our 16 total. We can't go beyond this. So it is recommended to begin on the outside of both of these atoms, and then if you have extras, go on the inside. So you get 4, 5, 6, 7, 8, 9, 10. Notice we add in a manner to make sure each element has 8. 11, 12, 13, 14, 15, 16. That's it. We've exhausted our number of electrons, but carbon does not have an octet. So we'll ask each of the oxygens to share a pair of electrons. So we'll ask this oxygen to pull this pair in, and this oxygen will pull this pair in. This again allows the oxygen to still keep its 8. It's just moving into a different location, but now carbon has the possibility of having an octet. So this becomes a double bond, this becomes a double bond, these are scratched out. So notice if we analyze the molecule now, this oxygen has 8 electrons, this carbon has 8, this oxygen has 8, we are good. It's a bit messy, but it would look essentially like this. All right, let's try the next few. Let's try SO4 2-. So first of all, go ahead and total up the number of valence electrons. From sulfur comes 6. From each oxygen comes 6. We have 4 of those. 24 plus 6 gives us a total of 32. We'll put sulfur in the middle with the 4 oxygens around the outside arranged. And then start adding electrons around the outside until we get to 32. So we have, so far we have 8, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. And this one actually is complete. Every element has 8. If you analyze it, we are good. Last thing to do, if you have a charge, it is customary to put brackets around the whole thing with a -2. This one's actually simpler. And the last one we'll do is HCN. Let's follow the same 5 steps. Total up the valence electrons. From hydrogen comes 1, from carbon comes 4, from nitrogen comes 5, for a total of 10 valence electrons. In this case, also put the carbon in the middle, and the formula gives you a clue to that. But if you take a look, hydrogen can never go in the middle because it can only have 2 valence electrons around it. The nitrogen is more electronegative. You'll never put in the middle of the molecule the more electronegative one, because electronegative elements want to pull electrons from others, so they won't put themselves in the middle where the electrons are pulled from them. So just arrange them like the formula says. That gives us 4 so far, 2, 4. Put them around the outside. So 5, 6, 7, 8, 9, and 10. That's it. We cannot do anything else. Carbon still needs an octet. So far it has only 4. So we'll ask nitrogen to pull both of its electrons in. This again does not decrease nitrogen's octet, but increases carbon's. So essentially we'll have a triple bond between nitrogen and carbon. And this then would be the formula. So hopefully that makes sense. The next idea that we'll cover in this lesson is something called formal charge. Now this is new, so it will allow us to determine which structure is the best. So here we have the CO2 molecule that we've drawn above. We've drawn it like this, but you can also just as easily draw it in this manner, where you have a triple bond on the right and a single on the left. Every element still has 8. This oxygen has 8. This oxygen has 8. This carbon has 8. It all works out still, but this is not the molecule, how the molecule exists. It actually exists like so. And something called formal charge will allow us to distinguish between these two. So let's define what formal charge is. Essentially, it's a calculation of the charge on each element. And the way we calculated it is we first count the number of electrons in lone pairs and half of the electrons in bonded pairs, or pairs it shares with other atoms. And we'll subtract that from the number of valence electrons for the atom. So again, it's the number of valence electrons that the atom brings. If you take a look at oxygen here, oxygen brings 6 valence electrons from the periodic table, minus the electrons bonded to the oxygen. So if you take a look here, these are oxygen's electrons, these are oxygen's electrons, and then half of these are oxygen's electrons. So there's 1 and 2 here. So for a total of 6. I know that's a bit messy, but we have 6 valence electrons there for the oxygen. That's why 6 belong to it in the structure. So you take how many it brought minus how many belongs to it, and that would be the formal charge. Same thing for the carbon. If you take a look at the carbon, let's see if we can make it a little less messy. Carbon has brought 4 from the periodic table, and here in the bond, 2 of these belong to it and 2 of these belong to it, because half of the bond is yours. So carbon has 4 in the bonding arrangement, formal charge of 0. This oxygen is the same as the one on the left, but if we analyze the second structure, we'll find that oxygen still brought 6, but in this case, 7 are his in the structure. These are his. Anytime you have pairs that aren't bonded, aren't shared with anyone, those are yours directly. And half of these are oxygens, which means this one electron is oxygens. That's how we get the 7, for a total formal charge of -1. Let's apply this to an example, and you can analyze the other 2 atoms as well. But the rule for formal charge is that the best structure is the one with the fewest formal charges, and the one that puts the negative formal charge on the most electronegative atom. So in this case, this structure has all zeros for the formal charge, so it is more stable versus having a -1 or a +1. Because in order to keep these charges separated, the molecule has to, you can say, use energy, and that will not be a stable conformation. It'll be more stable if all of them are equaled out. The electrons would rather be everywhere equally than more on one side and less on the other side. Think of it this way. So let's try an example of this. Here we're asked to draw 3 possible structures of the NCS- ion and determining, using formal charges, which is the most stable. So let's do this on the next slide. Let's first of all draw out NCS-. Let's total up the number of valence electrons. In this case, we have 5 from nitrogen, 4 from carbon, and 6 from sulfur. And then this is a -1 charge, so we get 1 more. So we have essentially 16 total. We'll put carbon in the middle and the sulfur on one side, the nitrogen on the other side. We have 3 of these to draw, so let's do the same thing here. And we have 1 more to draw. Do the same thing here. Okay. We got 16 total, so let's start putting them around the outside. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have to stop. Now we have to put double bonds on carbon. There are a few ways of doing this. We can either ask nitrogen to share both of its electrons, we can ask sulfur to share both of its electrons, or we can ask each one of these to share just 1 pair. In fact, let's do that. Let's draw these 3 possible structures. So apologize for the backtracking there, but we'll have one with a triple bond and a single bond, we'll have one with 2 double bonds, and we'll have one with a triple bond and a single bond reversed. And then the rest of these must be lined up, like so. So these are the 3 possible structures. Pause the video and take try to draw these on your own if this is confusing, but this should be the 3 possibilities. Now, in order to determine the formal charges, or which is the most stable, we have to calculate formal charges. For this carbon, carbon brings 4 from the periodic table. Here, 1, 2, 3, 4 are his, because half of these bonding electrons are carbons. So 4 minus 4, carbon has a formal charge of 0. Here, sulfur brings 6. In this case, 1, 2, 3, 4, 5, 6, 7 are his. So 6 minus 7 gives you a -1 formal charge. Nitrogen brings 5. Here, 1, 2, 3, 4, 5 are his, so this formal charge is 0. If you analyze likewise, you'll find that this carbon has a formal charge of 0. The sulfur here is 0. The nitrogen here is actually 5 minus 6, gives you a -1 charge. This is -1. And this carbon is 0. Sulfur is actually 6 minus 5, which gives you 1. And nitrogen here is 5 minus 1, 2, 3, 4, 5, 6, 7. Which gives you -2. Oops, it should be -2. So the way to pick between these 3 then is ask ourselves which one has the least formal charges and which one has the more negative on the more electronegative atom. And that would be this structure right here. This is because nitrogen is more electronegative than sulfur. Sulfur here has a negative charge, But because nitrogen is more electronegative, this is the best structure. And this completes for